Hello everyone, my name is Sean. Today I'm going to present our work Paxing Fast Performance Model for Graphics Workload on Mobile GPUs. This is a joint work with my colleague Chunling Hu and Chuchao Lin at Qualcomm. This is the agenda of this talk. I'll start with the introduction of our work, followed by a brief background session. Then we move on to the design of our model, and I'll show you some results. In the end, I'll give the conclusion of this work. Performance models are needed in many places. We rely on them to make decisions in our prototypes. It helps us find bottlenecks reasons, enables new designs and trade-off studies, and help us make better software. For performance model, we want it to be as fast as possible. No one likes to spend days to get the results back. We also want the results to be as accurate as we can get. You certainly don't want to build your work on a performance model with a questionable accuracy. The result has to be informative and insightful to help us better understand the system. The model itself should also be easy to use at a low cost. It covers a wide range of targets for us to play with, and when in need, easy for the users to make changes for their own research. However, it is hard to satisfy all these requirements. The prevailing performance models, analytical model and architecture model, both have their own weaknesses. Analytical models are easy to implement, fast at execution, but are usually not very accurate. On the other hand, architectural models work at cycle level. They can get cycle accurate, but usually at a huge cost of execution time. In some cases, it can take days or even weeks to finish a simulation that only takes a few seconds on real hardware. Architectural models can get faster with implementations on hardware such as FPGAs, but these solutions are usually costly, not friendly to users, and are often hard to make even simple changes. Besides the requirements we just mentioned, there are new issues in GPU performance modeling. GPUs have to deal with a huge amount of data in a short time window. To handle such demanding workloads, GPUs have many identical cores work at the same time. But even with high level of parallelism, it is still not fast enough for certain tasks. So we need to use some dedicated hardware. These are all new challenges we need to overcome when building a fast and accurate GPU performance model. Now let's dive a little bit deeper, move on to the background of this work. First, let's take a look at the classic graphics rendering pipeline. The input of the pipeline is a set of 3D models, which are described by vertices or a collection of vertices, also known as primitives. The first step is to process the positions and other associated attributes of vertices and primitives, which is handled by the vertex shader. The output of vertex shader is given to a dedicated hardware unit called rasterizer, which can produce many fragments from 3 vertices. These fragments are collected and sent to fragment shader to get their color. In the end, we merge the colored fragments and display the model in a 2D display. As you can see, from 3 vertices, we can get a much larger amount of fragments. We profiled a set of benchmarks and the result shows fragment shader is the major workload contributor. In our study, 98% GPU workloads comes from fragment shader. Therefore, our focus is modeling the performance of fragment shaders. In the graphics rendering pipeline, users have no control on certain stages, such as rasterization and blending. These stages are handled by dedicated hardware. On the other hand, the vertex shader and fragment shader are programmable, which are handled in streaming processors. A streaming processor has several execution units, such as arithmetic logic unit, control flow unit, special processing unit, load store unit, and texture unit. Each streaming processor also has their own register files, L1 cache, and a fast shared memory. Now let's see how the workload is distributed and executed on a GPU. Take fragment shader for example. Each fragment is mapped to a work item, a set of work items grouped together as a wavefront. With multiple wavefronts, we have a work group. The work items in each work group are dispatched and processed by a single SP, and the wavefronts in a work group is dispatched to SP in batches. Now you know how the graphics pipeline works. Let's move on and see how we design our model. First, let's refresh our memory on the requirements of a performance model. We want to build a performance model that is fast, accurate, informative, easy to use, covers a wide range of processors, and easy to make changes. To make it run fast, we first reduce the number of pipeline stages in our model. A typical architecture model simulates the whole pipeline stages. However, it is a common practice to match the width and buffer sizes between stages. Once the instruction is issued, no back pressure is expected. Therefore, we can only model the pipeline until issue stage, which reduces the execution time at no cost of accuracy. Second, there's no functional simulation in our model. Because we find there's no branch instructions in most shaders of our interest. For the outliers, we can read PC traces from other functional simulators. Our model works at cycle level. We found that in cycle-by-cycle simulation, many simulation cycles are idle cycles. In some extreme cases, 93% of simulation cycles are idle cycles. Our model is event-driven, so there's no idle cycles during simulation. Next, for some hardware units with deterministic behavior, we replace the simulation with simple and fast analytical models. Besides, the memory model is also simplified to a static latency model. Lastly, we use the aggressive execution to further reduce simulation time. In the graph on the right, the x-axis is the wavefront ID, the y-axis is the execution cycles of a wavefront. We can see that wavefronts can quickly reach a stable state. Therefore, we can only execute the first few waves and estimate the rest. The cost of accuracy is small even though we cut some corners. Thanks to the unique characterization of our workloads, there's no branch in most shaders, so there's no need for functional simulation. The memory access pattern is also very regular in these shaders, so we can use a simplified memory model with static latency. We also make the analytical models closely match our hardware design to keep a minimum impact to the accuracy. We also studied the impact of aggressive execution to accuracy. The simulation accuracy only drops a little, even if we reduce the workloads by 1,000 times. Besides good speed and accuracy, our model provides reports with 3 levels of details. Users can get a brief summary, detailed performance statistics, or complete simulation trace. It is easy to use, which only requires 1 input and 3 configuration files. The 1 input is the shader object file generated by our offline compiler. Users can set up the simulation with 3 configuration files in YAML format. The hardware configuration file is used to describe GPU hardware, such as register file size, resource bandwidth, and pipeline latency. The execution configuration file is used to set the number of waves to execute, the maximum simulation cycles, and PC trace. We also provide an optional software configuration file to override some simulation parameters, which by default are calculated from the shader objects file and the hardware description file. With these configuration files, we can easily cover several generations of our GPUs. The model is also easy to make changes because of its modular implementation. The centerpiece of a model is the SP. SP has an event queue with many events. An event describes tasks to perform at a certain cycle. Events are popped out of the event queue in ascending order of their cycle. An event may fetch instructions from instruction buffer to a wave, add new wavefront to the wavefront pool, or change state of a wavefront, or ask wavefront scheduler to issue instruction to an execution unit. An event can also add a future event in the event queue. We keep popping events out of the event queue. When there's no event in the queue, the whole simulation stops. Now let's move on and see some results. We selected the 19 fragment shaders from popular mobile games to evaluate our work. The selected shaders are the performance-dominating ones from critical scenes in those games. The Qualcomm Adreno 640 GPU is our platform for evaluation, which is a premium-tier GPU in Qualcomm Snapdragon 855 SoC. We use slowdown to evaluate the speed, which is the time a shader spent on the simulator versus it on real GPU. For accuracy, we compare the wavefront execution cycles on simulation versus cycles obtained by hardware performance counters. We did the on-device measurements in temperature-controlled environments. We also did multiple runs and averaged the result to reduce the noise in the data. So the first question is it fast? With aggressive execution, on average, our model is only 4.1 times slower than native execution. The worst case is also only 15 times slower. Because we only execute a small subset of wavefronts with aggressive execution, in some cases, our model can run even faster than our real GPUs. Comparing to other popular GPU architectural performance models, it is several orders of magnitude faster. This may change if we choose a faster GPU as our platform, but still, it will be much faster than traditional architectural models because of the choices we made for our model. Next question is on accuracy. We compare the on-device measurement versus simulation on wavefront execution cycles. In this figure, the x-axis is the shader ID. Y-axis is the wavefront execution cycle. As you can see, simulation cycles are pretty close to on-device measurements. On average, our model has a small error rate at 6%. We do have a few outliers. The peak error rate is at 27.9% in shader 7. It is largely caused by the analytical model for the wavefront initialization, which is highly sensitive to input data for graphics workload. The result shows the error rate is low for most shaders, and we have high simulation speed, which suggests that we have made good trade-off decisions for our model. In the end, we provided 2 case studies to show how our model improves our understanding of the GPU system. The first case study is on software. We made some changes in the instruction scheduling policy in the compiler. It improves performance on some shaders, but at the same time, it also caused a regression, and we want to know why. We compared the breakdown of store reasons before and after the change. In this figure, the x-axis is the shader ID. ID ends with V0 is before compiler changes. V1 is after the change. The y-axis is the percentage of stores. As you can see in this figure, the compiler tweak shifted contention in low store unit to LU unit for shader 4. However, such change in compiler has the opposite effect on shader 6. We can see low store contention takes a larger proportion, while LU stores now takes a smaller proportion. It also leads to less proportion of sync stores. This observation can help us to improve the compiler heuristics. The second case study is on hardware. In this case study, we take a look at the resource utilization imbalance issue. We take the first 8 wavefronts from a simulation run and studied the cycles they are stored by ALU and texture unit. In this simulation run, only 4 wavefronts can run at the same time, so wavefront 1 to 4 started execution one by one. When they finish execution, they retire and hand over the resources to pending wavefronts. It is clear that ALU utilization is imbalanced among wavefronts. As you can see, wavefront 1 has much fewer ALU store cycles than wavefront 2, which is fewer than the wavefront 3. This is because the older wavefront is given a much higher priority than newer ones. Newer wavefronts have to wait much longer for their turns to use ALU. In comparison, this imbalance issue is not so evident for texture unit. Identifying this issue and its differences inspires us to explore better dispatching and scheduling policies in GPU. Now let's conclude the work. In this work, we presented a cycle-level performance model for starting graphics workloads on mobile GPUs, which is a hybrid model that takes advantages of the architectural model and the analytic model. It has been validated against commercial mobile GPUs, which achieve a good balance between speed and accuracy. It offers accurate insight into GPU systems for the users to pinpoint bottlenecks, performs optimizations, and explore architectural changes. That is all for the presentation. Thank you for your interest in our work.